You've heard the saying, right? A diamond is forever? Well, what if I told you that's not entirely true? In fact, every single diamond out there is on a super slow journey to becoming, of all things, the stuff in your pencil. It sounds crazy, I know, and it's a paradox that we can only unravel by looking at two totally different fields of science.
So, check this out. On the left, you've got this gorgeous, priceless diamond. And on the right, good old graphite. You know, the stuff that's in your pencil. Now, here's the wild part. Chemically, these two are identical. Seriously, they're both just pure carbon. So how on earth can one be the hardest thing we know of, while the other is one of the softest?
Okay, so this is where the real puzzle kicks in. Basic physics tells us that right here, right now, under everyday conditions on Earth, the diamond is the unstable one. It actually wants to turn into graphite. So why isn't it? Why is that diamond ring still sparkling instead of turning into a smudge of pencil lead?
To get to the bottom of this, we've got to talk about a diamond's big, unstable secret.
It sounds completely backward, I know, but here's the deal. At the normal pressure and temperature we live in, graphite is the more stable form of carbon. A diamond is actually stuck in this high energy state. And one thing about nature is it always wants to find the path of least energy. So yeah, that means every diamond out there is thermodynamically destined to become graphite.
The key to this whole mystery isn't just one answer, it's actually two. We need to ask two totally different questions, and each one gets answered by its own special field of science.
So, first up, let's talk about thermodynamics. This is the science of what's even possible in the first place.
Think of thermodynamics like this big cosmic judge that gives every potential reaction a simple thumbs up or a thumbs down. It doesn't care how long it takes or how fast it goes. All it asks is, can this thing happen at all? It just looks at the energy of where you start and where you end up.
And this brings us to a really important idea called free energy. You can just think of it as a way to measure stability. A reaction is considered favorable, meaning it gets that thumbs up from thermodynamics, if the thing you end up with is more stable or has lower free energy than what you started with.
The classic example is a ball sitting at the top of a hill. It's got a lot of potential energy up there, right? It's not super stable, and it will naturally, spontaneously, roll down to the bottom where it has lower energy and is way more stable. Well, chemical reactions work on the exact same principle. They want to roll downhill, energy-wise.
So let's bring this back to our diamond. The diamond, that's the ball at the top of the energy hill. It's in a high energy state. And graphite, that's the nice, stable valley down below. So the journey from diamond to graphite is all downhill. Thermodynamics looks at this and gives it a giant thumbs up. It's basically shouting, yes, this can happen. This should happen.
Okay, but if that's true, why are we not all wearing graphite rings? The answer to that comes from our second field of science, kinetics. You could call it the science of the practical.
It's a really simple distinction. Thermodynamics asks if it will happen. Kinetics asks, okay, but how fast? It's all about the speed. It's the science that looks at the actual path a reaction takes and how quickly it moves along.
And here's the punchline. While thermodynamics is screaming, yes, this can happen, kinetics steps in and says, whoa, hold on. The speed of that reaction is so ridiculously, unbelievably slow that for all practical purposes, it's just not happening.
So why so slow? Well, it turns out that even when you're going downhill, sometimes you've got to get over a pretty big bump first.
Take a look at this graph. See, on the left, we start at a high energy level, and on the right, we end up at a lower one. It's a downhill journey overall. But you see that giant hump in the middle? To actually get to the finish line, you first need a big push to get over that hump.
That hump has a name. It's called the activation energy. It's this energy barrier you have to get over just to get the reaction started. It's like the minimum investment of energy you have to put in before you see any return.
And it's really straightforward. The bigger that hill, the slower the reaction. A tiny little hill, super fast reaction. A gigantic, mountain-sized hill, you guessed it, an incredibly slow one.
And when it comes to a diamond turning into graphite, that energy hill isn't just a hill, it's Mount Everest. You see, the carbon atoms in a diamond are locked into this super strong, super rigid 3D structure. To turn them into the flat sheets you see in graphite, you first have to break all those incredibly powerful bonds. And that takes a colossal amount of energy. It creates a massive activation energy barrier.
But, scientists are a clever bunch.
They've figured out ways to deal with these energy hills and, speed things up a bit.
Basically, there are two main ways to do it. The first one is brute force. You just add a bunch of energy, usually heat. That gives the molecules the extra oomph they need to scramble over the top of the hill. The second way is a little more elegant. You use something called a catalyst, which is like finding a secret tunnel through the hill.
If we look at our diagram again, you can see what I mean. A catalyst doesn't try to push the reactants harder over the big hill. No, it actually creates a brand new path. That's the dotted line there. It's a new route with a much, much lower hill, which makes the whole reaction happen way faster.
And this isn't just some abstract science concept. This is absolutely essential to our modern world. We use catalysts for everything, making the fertilizer that grows our food, refining the gasoline for our cars, and even in the catalytic converters in those cars to clean up the exhaust. They're everywhere.
All right, so let's tie this all together. What's the big takeaway about things that look stable, but maybe aren't truly permanent?
It really comes down to this. Thermodynamics asks the big picture question, will it happen? It's all about getting to a more stable place. But kinetics asks the practical question. Okay, but how fast? It's focused on that energy barrier, that hill you have to climb. You absolutely need both to get the whole story.
So there's actually a scientific term for materials like diamonds. They're called metastable. It means they're stable enough for our purposes, but they're not in their ultimate stable state. It's kind of like a ball that's not at the very bottom of the valley, but is just resting in a small dip on the way down. It's stuck there for now. Window glass is another perfect example of this. It's actually a supercooled liquid that is very, very slowly flowing downwards over hundreds of years.
So, a diamond is thermodynamically unstable, but it's kinetically super, super stable. And that kind of leaves you with a cool thought, doesn't it? It makes you wonder, what else out there in the world seems totally permanent, but is really just sitting there, waiting for the right little push to get over its own energy hill and change into something completely different? It's a pretty wild idea to think about.